Okay, I'm going to work out some problems from Chapter 11 for gas laws. Most of these problems are pretty straightforward. Stuff that you learn to do probably in pre-algebra. One thing we have to do first, we're going to be working with pressure, volume, and temperature. Our pressure always needs to be in the units of atmospheres. Our volume needs to be in liters, and temperature needs to be in Kelvin. Sometimes a number will be given to you in milliliters, and to go from milliliters to liters, we move your decimal 3 times to the left. So that's something that we learned way back in the very first chapter. Temperature. Usually the temperature is given to you in Kelvin. If it's given to you in Celsius, use this formula. That one shouldn't be new to you either, something that we learned in one of our earlier chapters. But to get our units in atmospheres, this is something brand new. It's in section 1, I believe, of chapter 11. It's on page 364. And we'll talk about the different units that you can have for pressure. It's easier for us to change our units of pressure to atmospheres. It will help us later on with one of the ideal gas laws. So on page 364, you'll see that 1 atmosphere, which is standard, is also equal to 600 millimeters of mercury. We get this off of a barometer, and it's actually, that's how many millimeters high the mercury is in that barometer. 1 atmosphere can also equal 760 torr. It's also equal to 1.01 times 10 to the 5th kilo. No. Sorry. 1.01 times 10 to the 5th pascals, or 101.3 kilopascals. So those are the different units. There's more than this. There's another unit called bar. You won't see it in your book, but that would be something that you could possibly see in college chemistry. If I tell you that we have 800 millimeters of mercury, before you even start your problem, you need to change your millimeters of mercury into atmospheres. So to do that, we set up a real easy conversion box. And from here, we know that there's 760 millimeters of mercury in 1 atmosphere. So we're going to put 760 millimeters of mercury on bottom, so it'll cancel out. We will put 1 atmosphere on top, and then you're going to get out your calculator and divide your 800 by 760, and you get 1.05. So then in your problem, instead of using 800 millimeters of mercury, you're going to use 1.05 atmospheres. All right, so now, with that little quick introduction, we'll start on some problems. These very first ones are from Boyle's law. In Boyle's law, we are comparing pressure and volume. And so the formula that they give you, P1 times V1 equals P2 times V2. We want to make sure pressure is in atmosphere, volume is going to be liters. And we can look at this too. If we're multiplying, then that means that if our pressure increases, our volume is going to decrease. So we need to look at that when we get to our answers to make sure it matches up. All right, so what I like to do is I'm reading through the question. I like to label each one of those numbers as being P1 V1 or P2 V2. All right, so 1 liter of gas. Liter automatically tells me that's a volume, so I'm going to label that one as V1. Move it down a bit. It's a 1 liter of gas at standard temperature and pressure. It's compressed to 473 milliliters. So milliliters, that's the volume. So I'm going to label that as V2. In the middle of that question, or that sentence, it says standard temperature and pressure, and that's something that you did on a worksheet in the last chapter. standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere. There's not any temperature in our formula. P1 times V1 equals P2 times V2. So we don't need temperature. We can just ignore that. But this pressure, we have 1 liter of gas. It's at standard pressure, so that means our V1 is going to match up with this P1. And the question asks, what is the new pressure of the gas? So that means we're solving for P2. So now we just need to plug our numbers in. So P1 is 1 atmosphere, and our V1 is 1 liter. We don't know what P2 is. That's what we're going to solve for. And V2 says 473 milliliters, but we need to change that to liters because liters and milliliters won't cancel. So to do that, I need to move my decimal 3 times to the left. So I end up with 0.473 liters. All right, so now we plug this into our calculator. I want P2 by itself, so I'm going to divide each side by 0.473 liters, and it cancels there. My unit of liters cancels out, and I'm left with units of atmospheres, which is good because that's how we measure pressure. And so P2 should equal 0.002 atmospheres. Make sure you put units on every single answer. So that's our answer for P2. All right, let's do another one. In a thermonuclear device, the pressure of 0.050 liters of gas, so liters tells me volume, so I'm going to label that as V1, within the bomb casing reaches 4 times 10 to the 6 atmospheres. So I'm going to label that one as P1. When the bomb casing is destroyed by the explosion, the gas is released into the atmosphere where it reaches a pressure of 1 atmosphere. So that's a pressure, so that's P2. What is the volume of the gas after the explosion? So now we're solving for V2. So now we just plug in our numbers. Hands off for V2. All right, so I want V2 by itself, so I'm going to divide each side by 1 atmosphere. You do your algebra any way you want to. My units of atmospheres cancel out, and I'm left with units of liters, which is good because I'm solving for volume. So 4.0 times 10 to the 6 times 0.05, divide that by 1, and you should get that V2 is equal to 200,000 liters. And if we look at this, our pressure has dropped significantly. It went from 4 times 10 to the 6. So if we move our decimal 6 times to the right, and it dropped all the way down to 1 atmosphere. So if our volume was 0.05, it should greatly increase. And it does. So that makes sense. That's really all there is to it for Boyle's law. You're just comparing pressure and volume. All right, going on to the next one. This one is called Charles's law. And in Charles's law, we're comparing volume and temperature. So in the book, they give you V1 over T1 equals V2 over T2. So we want our volume in liters, we want our temperature in Kelvin. And we can see right off the bat in this problem, I see degrees Celsius 2 times. So that's something we're going to have to change. So the temperature inside my refrigerator is about 4 degrees Celsius. Okay, so I can label that as T1. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius, right, so that's T2, and a volume of 0.5 liters. All right, 0.5 liters is going to be P2. It says it's at 22 degrees Celsius and at 0.5 liters. So even though this is the first volume listed, it should be matched up with 22 degrees Celsius. So this is why I'm going to label this one V2 instead of V1. So now, first thing we have to do before we can plug these in, we have to change them to Celsius. And I should finish reading the question. What will be the volume of the balloon when it is fully cooled by my refrigerator? So we're solving for V1. So we have to take our 4 degrees Celsius, that gives us 277 K. Our V2, 0.5 liters, and then 22 degrees Celsius plus 273 would give us 295 K. So we need to solve for V1. So I'm dividing by 277 on the left. I want V1 by itself. So I'm going to multiply this by 277 and it cancels. And I'm going to multiply this side by 277K. And we plug this into our calculators. And you should get that V1 is equal to 0.47 and its volume. So that should be liters. Our Kelvin cancel out here and we're left with liters. And this should kind of make sense because if temperature increases, volume is going to increase. So then volume should increase. So if our temperature went from 295 to 277, it decreased. So then our volume should decrease. So our answer should be less than 0.5. So that worked correctly. All right. Our next one. A man heats a balloon in the oven. If the balloon initially has a volume of 0.4 liters, so that's our V1, and a temperature at 20 degrees Celsius, that's T1, what will the volume of the balloon be after he heats it to a temperature of 250 degrees Celsius? So that would be T2, so that means we're solving for V2. All right, so 0.4 liters. So then we need to add 20 degrees Celsius to 273, which gives us 293 Kelvin. We are trying to solve for V2. And then our T2, 250 plus 273 gives us 523 K. So if our temperature is increasing here, then our volume should also increase. So we should get an answer that's above 0.4. So we're going to multiply each side by 523K. See if I can get this to... And you should get an answer of 0.71 liters. Kelvins cancel, we're left with liters. So that is right. Our volume has increased. Right, that's really all there is to Charles's law. And most of you will look at this mathematically as cross multiply and divide, which works fine. Just be careful when your variable, what you're trying to solve for, is in the denominator. Our next type is Gay-Lussac's law. He compares pressure or temperature to one another. And so his law is P1 over T1 equals P2 over T2. And this should be as our pressure increases, our temperature also increases. So a cylinder of gas has a pressure of 4.4 atmospheres. Atmospheres tells me pressure, so that's P1. At 25 degrees Celsius, that's T1. At what temperature in degrees Celsius will it reach at a pressure of 6.50 atmospheres? So that's P2. we're looking for T2. So 4.40 atmospheres divided by 25 degrees Celsius plus 273 gives me 298 K. We have 6.50 atmospheres divided by T2. Solving in the denominator. One thing that you can do is flip each side so that you're not solving in the denominator. I'm not going to go through the algebra for this because I was taught something differently than you were. So you multiply and divide. Set up your algebra the way you need to. You should get a temperature of 440.2. If you can't get this in the calculator, come see me. And then I will look to see how you do algebra, and then I'll show you what the next step should be so that you can get this correct. Our units of atmospheres cancel. We're left with Kelvin. If you notice, our pressure decreases. So our temperature, wait a minute. Pressure increases. We're going from 4.4 to 6.5. So our temperature should also increase, going from 298 to 440. So that one checks out. All right, and then the next one. A cylinder of compressed gas has a pressure of 4.882 atmospheres, P1, on one day. The next day, the same cylinder of gas has a pressure of 4.690, and that's P2, and its temperature is 8 degrees Celsius. So if the pressure, if we labeled it as P2, this temperature has to be T2. What was the temperature on the previous day in degrees Celsius? So we have to solve for T1. So 4.882 atmospheres over T1 equals 4.690 atmospheres. And then we have to do 273 plus 8, which would give us 281 K. Again, we're solving in the denominator. Our units of atmospheres will cancel. We'll be left with units of K, which you should get 292.5. If you can't get this in the calculator, please come see me so I can help you with it. All right, so let's see. Our pressure increased from 4.69 to 4.882. And so that means our temperature should also increase 281 to 292. So that one worked out. All right. Our next gas law is called the combined gas law. So we're going to take Boyle, Charles, and Gay-Lussac's, and we're going to put them all together in one big formula. So we're just combining them all together. And it is P1 times V1 over T1 equals P2 times V2 over T2. The only thing that's challenging about this is keeping up with all your numbers. So if I initially have a gas at a pressure of 12 atmospheres, P1, a volume of 23 liters, V1, and a temperature of 200 K, T1, and then I raise the pressure to 14 atmospheres, P2, and increase the temperature to 300 K, T2, what is the new volume of the gas? All right, so all of our units are correct. We have atmospheres, liters, and Kelvin. So really all we have to do is plug this in. So we have 12 atmospheres, 23 liters. Divide that by 200 Kelvin. That is equal to 14 atmospheres. We don't know what V2 is, and T2 is 300 K. All right, you do what you need to do on your algebra. You'll end up multiplying 12 times 23 times 300, get an answer. And you will multiply 200 times 14 and get an answer. And you will divide those two values. And you will get that V2 is equal to 29.6 liters. Because we have so much going on, it's really hard for us to look and compare to say, okay, well, temperature increase, so our volume increase. Well, pressure increase, so volume increase. This one gets kind of tricky. So we need to be very careful with our math and check it as we go. All right, the next one. A gas takes up a volume of 17 liters, V1, has a pressure of 2.3 atmospheres, P1, and a temperature of 299 Kelvin, T1. If I raise the temperature to 350 Kelvin, so T2, and lower the pressure to 1.5 atmospheres, T2, what is the new volume of the gas? So again, we're solving for V2. All of our units look correct. We've got atmospheres, liters, and Kelvin, so we can just plug these in. 2.3 atmospheres and 17 liters. All of that's over 299 Kelvin. And we set that equal to 1.5 atmospheres. We're solving for V2. We don't know what that is. And then 350K. All right, so rearrange your variables, simplify. You're going to end up multiplying 2.3 times 17 times 350 and get an answer. Multiply 299 times 1.5 and get an answer. And divide the two values. So V2 should equal 30.5 liters. So really on all of these problems, they're just plug and chug. I give you numbers for every single variable except for one. You do the algebra and solve for the last one. All right, and then our last type of problem, this is called the ideal gas law. PV equals nRT. N is number of moles. R is a gas constant, and it will always be 0.0821. If you look in the book, it gives you multiple values for R. I think that's in section 4. If you use units of atmosphere for pressure, 0.0821 is the only R value you need to know. The value of R changes if you have different units for pressure, but since we always use atmospheres, we don't need them. So we're going to do the same thing. We're going to go through our problem. We are going to label every number and then plug it in. If I have 4 moles, so that's N, of a gas at a pressure of 5.6 atmospheres, that's P, and a volume of 12 liters, that's V, what is the temperature? So we're solving for T. So I'm going to start with 5.6 atmospheres times 12 liters equals 4 moles times our constant of 0.0821, and the units for this are atmospheric liters over mole Kelvin, and your book goes over all of that with you. And then T for temperature, and that's what we're solving for. So we want temperature by itself. We want to move this to the other side of our equation, and you could simplify this first if you wanted to. And if we go through and we cross, moles cancel here, atmospheres cancel, liters cancel, and we're left with just Kelvin. We can put this in the calculator. You should get that temperature equals 204.6 Kelvin. Right. And I will do one more with you. If I have an unknown quantity of gas at a pressure of 1 atm, a volume of 31 liters, and a temperature of 87 degrees Celsius, how many moles of gas do I have? So I'm solving for N. So now all I have to do is plug my numbers in. 1.2 atmospheres, 31 liters, don't know what N is. R is 0.0821. Oopsie. Let me do this. 0.0821 atmospheric liters over mole Kelvin times, all right, so it's 87 degrees Celsius. We need to convert that to Kelvin, so we need to add 273. You should get 360 Kelvin. So we want N by itself. So that cancels. Now we bring it over here. All right, so atmospheres cancel, liters cancel, Kelvin cancels, and we're left with moles. So if you plug this into your calculator, N equals 1.3 moles. All right, so that's an example of how to solve 2 of every type of problem for Chapter 11. If you have any questions, please come see me.